Hello everyone, good afternoon. Today is the first video of our new series of remote lectures due to the coronavirus. I'm sorry about the delay. I haven't been able to post videos for the first few days, the first couple of days. I was planning to start on Monday, but I had some technical difficulties along with kind of getting a workflow going that will allow me to both talk about these things and also mark up the PDF like a whiteboard. I think I have a good system fixed now, so we'll see how this works. So we'll start talking about the idea of robustness in today's lecture. Uh, this is where we left off before classes ended. We were just about to start this. So what I'm going to do is today and probably tomorrow as well, we'll talk about chemotaxis. So that's the bacterial system of chemotaxis and how it's robust to uh, levels of proteins, etc., as an example, and to kind of give the idea of biochemical robustness and what's involved. We'll go to another example of a different kind of robustness, the robustness to mutation or copy errors, and the idea of kinetic proofreading. That's the second part of this module. And finally, we'll talk about fitness and adaptation and optimality and how biological systems create optimality. Uh, so hopefully when all these three sections at the top are done, we will be done with the subjects for this week. Normally this would have been done in class. So let's begin. So you have to define the idea of robustness before we move on. So the idea is you can think of robustness as the kind of the insensitivity of the 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 insensitivity of the basic essential features of any system to outside noise and some kinds of noise and to some extent of noise. So we see this kind of uh, in both biological systems and engineered systems as well. So, for example, your cell phone's radio is robust to electromagnetic noise. It can still talk to the cell tower and get its point across, even if there are other devices talking around it. If there is atmospheric noise, like a thunderstorm or something. So that's the essential feature being communication to the cell tower. The cell phone can still do that even when the conditions aren't perfect. Of course, there's a limit to how robust a system can be. If there is very high electromagnetic noise, obviously the cell phone won't work. Other examples are from our own bodies. For example, your insulin system is robust to fluctuations in your sugar intake and tries to keep the blood sugar level steady. But if you kind of, again, this is robust to a point. If you go up and eat 15 donuts at a time, it's not that robust. Um, so uh, the textbook, Alon's book, defines robustness as biological circuits evolve to have robust mechanisms such that their essential function is nearly independent of biochemical parameters that tend to vary from cell to cell. And so you have to think about what varies from cell to cell. The, the thing that varies most often from cell to cell is the amount of protein. So our first example will be based on that. Obviously, all cells have kind of similar amounts of a certain protein if they're in the same state, but best case scenario, from cell to cell, the amount of the protein will be a distribution. So let's say this is the perfect amount, the perfect molarity of some protein X. Some cells will have slightly less, some cells will have slightly more, depending on how lucky they were getting food and essential amino acids, etc. So you can't really trust that all cells will have exactly the perfect level of protein. Obviously, this is one example, and we know that although robustness is kind of a desired thing, not every system has to be uh, robust to everything, right? So not all functions of a biological system have to be robust. Some functions may be sensitive to certain inputs. Obviously, if they're designed to be or evolved to be sensitive to a certain input, they have to be. Even then, sometimes it's something that never came up, a new environmental condition, which means some systems are not going to be robust to that. But if the organism is evolved in certain environmental changes or internal changes, it generally evolves systems that are robust to those changes. And the other thing is, you have to remember that robustness is not absolute, meaning you'll never have a 1 or 0 decision of robustness. Some systems will be more robust to a certain kind of noise, other systems will be less robust, and so on and so forth. So robustness is relative. Okay, so now our example today will be chemotaxis in bacteria. This is the same example in the textbook if you have a copy. If not, I'm going to talk about it anyway. So we saw before that bacteria, especially E. coli, when we're talking about multi-FFLs, we said that it actually assembles flagella on its membrane. So if this is your little bacterium, it has little tails coming out of it. And this allows the bacterium to swim. The good thing about that is it can essentially, for example, you can do this as experiment. You take a bunch of bacteria, E. coli in this example, and you can basically take a pipette and drip an amount of some attractant, something they like sugar or aspartate. They'll actually start swimming towards where the pipette has just inserted the new thing. Obviously, there's going to be a gradient where you just pipetted the material. There's going to be a lot of concentration there, a little bit less outside, and so on and so forth. So the bacteria will be able to sense the direction which the concentration is highest, and we're going to talk about how they do that. It's kind of like, let's say you're sitting in the living room and somebody opens the kitchen door and suddenly there's a very nice smell of cookies coming. So you start walking towards the smell. Obviously, you know where your own kitchen is, but even if you didn't, you could just follow the smell to where the cookies were. So the same idea with bacteria. And the way they do this is by they don't swim directly. They rather do what we say is a biased random walk. So just to show you what that is, here's an example of a random walk. So let's say you're this little bacterium. You're over here, and you decide the only two options you have is rotate randomly or go straight. So, and you do this by changing how your flagella work. If they all turn together, then you go straight. You swim straight. Otherwise, you rotate randomly. So there's no steering wheel on a bacterium. And that makes sense because they're living in a relatively harsh environment. When you think about it, when you're an E. coli bacterium, you're about 1 micron in size. So everything is very large compared to you. Even water molecules are relatively significant. When they hit you at a certain speed, they change their direction. So just the impact of water molecules around it causes the bacteria to do some Brownian motion, meaning there's always some randomness involved in it, how it moves, how it has to move. So you have to think, you can think of it like yourself. You're trying to walk in a very powerful storm, right? You can generally walk generally in the direction you want, but you're going to be thrown around a bit. So same thing with bacteria. So they randomly either do a run, which means they go straight, or they do random turns. We call those tumbles. So typically E. coli tumbles once per second, but when it finds food, especially as it gets getting closer to food, it tends to tumble less. So let's say you're an E. coli bacterium again, and you just tumbled, and you started going straight. Now you sense that, let's say, food is getting better. So here's the kind of concentration of food. A lot of food here, a bit less food there, and so obviously these aren't like levels, but kind of there's a gradient towards the food. So you did your tumble and you started running, and you realize that the attractant is getting more concentrated. So what you do is now you decide, okay, I'm going good, so let me not tumble for a while. So I move again, and so on and so forth. You move to you tumble less and less. Maybe sometimes randomly you tumble, you start going this way. It's not changing, so you tumble again, so you start going that way. Now it's getting better, so you tumble less. The idea is you'll always tumble every now and then, but the rate at which you tumble changes if, as you're running, you're getting a signal that the food is getting more concentrated. Or conversely, it could be it might not be an attractant or something you don't like, some kind of pollutant, for example, nickel ions, etc., that they want to escape. They'll do the opposite. So you tumble less if the attractant is getting higher, and you tumble a lot otherwise. Now the question is, how do you know that the attractant is getting higher as you move? So before we get into that, here's another kind of illustration of how they tumble versus how they move. Remember how these flagella were built from a previous lecture. They're built of little protein segments that move in from the tube of the flagellum and assemble the flagellum from the inside. And remember that those protein segments weren't exactly symmetrical. So the flagellum is kind of like a little piece of twine. So if you twist it one way, it goes in wildly different directions, like this. And if you twist it the other way, it wraps around. So, for example, if the little molecular motor on the membrane decides to go clockwise on one flagellum, the flagella kind of break apart and each push in a different direction, which means you're tumbling. Otherwise, if the motors are turning counterclockwise, they wrap up and become one big impeller, which pushes the bacterium forward. So essentially, that's how it controls how it's going to move, or rather, how it's going to whether it's going to move forward or not. And essentially, it will have a bunch of these flagella, typically something between 5 or 10 of them. And if, like, for example, 5 of the motors decide that they're going to go counterclockwise, you're doing a full run. If some of them don't have enough signal and they do clockwise rotation, then you're going to start tumbling. Okay, so here's another kind of a micrograph of this happening. You can see the bacterium here with in the first panel, it's doing a run. Around the sixth panel, it's beginning to tumble. It tumbles from panels 10 to 15 or so, and then between panels 16 and 20, it's doing another run now in a different direction. So the question is, how does it know which way to go? So how would you kind of design a system, a bacterium, that could sense gradient, the change of kind of concentration as it moved? So the obvious kind of, oops, sorry. Okay, sorry about that. The obvious way to think that you can think of is, what if I was a bacterium again and I had sensors on two sides, right? And then I could say I calculate the kind of measure the amount of material here and measure the amount of material here and subtract them to figure out where to go, whether it's getting higher or lower between these 2 points, between A and B. The problem with that is, like, again, the bacterium is very small. And we've seen from experiments that they can figure out essentially a gradient of one molecule across their body length. So 1 molecule per microliters. If there's 1 molecule more here than in A, the bacteria knows it. The problem is there are typically of attractant about 1,000 molecules around it. So this distance of one micron is simply too small to get a good reading between A and B. So you can't really have two sensors that that take measurements and take the difference of those. You can't do that because essentially there's randomly molecules moving around, so that this distance is not enough to get this kind of 1 molecule per micron kind of gradient sensing ability, which is what they need. It's too noisy. So they have to do something else. So they can't sense gradient with two sensors on two ends of the bacterium. And the other question here is which two ends, right? So that's also a problem. There are cells that actually do that. So for example, some of your immune cells have different receptors on two sides, and they can sense the gradient of cytokines on and kind of go to where the inflammation is, but they are very kind of much larger cells, an order of magnitude order of magnitude of two larger than the E. coli bacterium. So their sheer size allows them to have two sensors on different sides, and the different sides are far enough apart that you can sense the difference. The bacteria is not that lucky. So we said it doesn't work. Too much noise because the cell is too small. So then the question is, can you keep track as you move? Meaning, remember what the previous level was, and then kind of at the next time step decide that it's gotten lower or higher. So what you need for that, obviously, is you need memory. You need to remember that the levels of attractant used to be different. I don't know, a microsecond before or a second before. So you're swimming, and if they're getting better, then you know. So kind of like, again, our example with your nose, you're walking around and the smell of cookies gets stronger then you know that you're getting closer. So that's pretty good. But we have brains, and obviously we can remember things. So the question is, how does the bacterium do that? Okay. So their idea of memory is they adapt to the current level biochemically, and then when the level they adapted to changes, then they can kind of do something about it. So if there's a change from what they adapted to, then they tumble more, for example. So, or tumble less in this case. So it depends on which way it changes, right? So if they've adapted to a certain molarity of sugar, say, and it gets higher, that difference causes them to tumble less. If they were adapted to a certain level of sugar and it got lower, now they're tumbling more. And that, along with the kind of idea of this biased random walk, will slowly push them towards where the food is or away from where the poison is. What's important there is you need to have what's called perfect adaptation or exact adaptation, meaning you have to, once you adapt, something changes, you readapt and you come back to the same level. Again, we can talk about this in terms of your nose. Let's say you found the kitchen, you found the cookies, and the kitchen is constantly kind of has a cookie smell in it. If you stay there for 5, 6 minutes, your nose will get used to it, and then you'll not smell the cookies anymore. But somebody new coming into the room will smell the cookies. That's what adaptation is. Your nose is essentially adapted to that nice smell, uh, so that you don't notice it anymore. Same thing with bacteria. So if you look at this, we can see perfect adaptation versus imperfect adaptation. Let's say initially there was a certain amount of food, and at a certain point somebody pipetted in new sugar into where the bacteria were, and suddenly the amount of food jumped. Now the bacteria were tumbling along maybe at 1 tumble per second or something like that. And the moment the food increased, their activity, the rate at which they tumble, the frequency at which they tumble suddenly dropped. So now they're tumbling at maybe 0 or close to 0 tumbles per second. And in time, this stays the same, and they start adapting. Now, in time, they tumble more and more because now they're used to this. Maybe they tumble once every once every 2 seconds, so half a tumble per second, uh, and then they come to a new steady state. Now the point is, if this new steady state is different from where they were before, it's not perfect adaptation. So let's say if they come to a new steady state where they tumble 0.8 times per second instead of the original one, then this is imperfect adaptation. So if you kind of increase the food again, they stop tumbling again, and then they start adapting. But again, this is now a different steady state than the original steady state or even the second steady state. And it goes both ways. Now, if the food drops back, they tumble even less, and they kind of they tumble even more for a while because they're trying to find the food again, and then they readapt. But again, this is different from what the original thing was over here. What would exact adaptation look like? It would be something like this. You'd have perfect adaptation where when the food increased, you decrease, but then when you adapt, you come back to the original steady state. And then if it increased again, you'd go back down, the activity, the amount of tumbling, so you'd do a straight run, and then soon your tumbling rate, your tumbling frequency would come back to the original steady state. And again, if it dropped back down, you'd get desperate, tumble a bit more than usual, but again, you'd come back to the original steady state. And this tends to be important. And I'll show you why with a nice simulator. Okay, so this is a very simple but nicely done simulation program by Nikhil Batta. This is the one in the top. This one is the actual URL. You can click this and go there, but that website tends to be down very often, so I also have a backup link from the Internet Archive that you can use if the first one doesn't work. So let's take a look at it. So now what he did here is he's simulating a bunch of bacteria. I think, how many of them? Let's see, number of bacteria, 20 of them swimming around. And the red color represents the amount of sugar. So the more red, the brighter the red, the more concentration of sugar. So it's like somebody just pipetted a bunch of sugar in the middle of the screen, and it kind of diffused outwards. And you can see the actual bacteria moving about. And also, if you look at the gray circle here, where it says where the bacteria hang out, you'll see kind of a heat map of where most bacteria have been. So now what I'm going to do is turn on adaptation. So in this case, these bacteria aren't adapting at all. So they're just constantly tumbling at the same frequency, which is set. So 50% tumble, and there's no adaptation. So if we open up adaptation, so it says tumble returns to steady state, but it's a linear steady state, so it's a proportional controller, which means there's always going to be an offset, meaning it's the imperfect adaptation we talked about. It will come back to the steady state, but not quite. There'll always be some error, and see how that performs. So I've restarted the simulation, and when you look at the animation, you don't really notice them doing all that much different, but if you look to the right side, to the heat map, to the where the bacteria hang out thing, you realize that they're now hanging out more often in the sugar-rich areas, which is good. I mean, it's what we want, except it's not, like we said, perfect. If they were to adapt to the exact right kind of steady state, they would be much more precise at it. And to simulate that, there's a third adaptation option here. He calls it no tumble up, tumble otherwise, a two-state adaptation, but it's actually pretty close to what we're going to talk about in terms of perfect adaptation. So you can always look at the details here. He goes through all the algorithm. It's not a differential equation system like we've been doing. It's a more discrete kind of if-then type of program, but it simulates what would happen if you did this with differential equations. So the details are, there's a link in the top right just next to the title, so you can click that if you're interested. So what happens if I do no tumble up, tumble otherwise two states? So if I simulate perfect adaptation, this is what happens. So they get much more, except for the one that got lost on the way. They're much more precise and effective at it. So that's the idea. If you can get perfect adaptation, you'll be less hungry, let's say.